Hello friends, IBM is here with another episode of Learning Physics, and today I would like to take you to another unit which is going to be called Solved Past Paper Questions. That is, specifically I want us to look at force, density and pressure. Remember, this is AS Physics, Physics 9702, that is Cambridge. Uh, but of course the questions may be overlapping with some of the questions in your curriculum in case you are not studying Cambridge. So you can also still use them for practice because physics remains physics. So we are going to deal with the questions, past paper questions under force, density and pressure. And I want you to note that we shall be seeing questions. We expect to discuss questions, or we expect questions about density as a concept, pressure as a concept. You may hear Upthrust many times. You may hear Archimedes' principle. You may hear moments or torque or even a couple, equilibrium of forces, center of gravity, and a lot more. So without wasting time, I want us to go straight away to the past paper questions so that we start solving them. Okay, so without wasting time, here is the document for past paper questions. To begin with, let's define density. I want you to note that the questions may overlap from one topic to another, so you'll bear with that because there is no clear difference between some of these topics. You may find a question that was in errors and uncertainties. You may find a question what was in in physical quantities when it is answered again. So it's hard to draw a clear boundary between these topics, so you'll bear with that. So let us start. Density, of course, you don't waste time defining density. Density is simply mass divided by volume. The mass per unit volume, that is density. The figure shows a pyramid with a square base. So this is a square base. That means the cross-sectional area is x times x, which is x squared. The mass of the pyramid is given by this expression here. We must have answered this question in uncertainties or in physical quantities and units, but we shall just repeat it for completeness. Rho is density, h is height, x is length. Measurements are taken as shown in the table. They've given us quantities of quantity m, x, and h. They are measurements and their percentage uncertainties. Then calculate the absolute uncertainty in x. So absolute in x, absolute uncertainty in x is going to be, we convert the percentage, that will be 5 divided by 100 times the value of x, which is 4.0 centimeters. So we can check this. 5 times 4 divided by 100. So the percentage, this is actually 0.2 plus or minus 0.2 as the absolute. The density rho is calculated from the measurements in the table. Determine the percentage uncertainty. So from the given expression, I'm going to make a density the subject to be able to find the percentage uncertainty. So from the expression given above, I think you notice that density is going to be equal to 3 times m divided by h x squared. So since there is division, there is a power, there is multiplication, we just sum up the percentage uncertainties. Therefore, percentage uncertainty in density is equal to percentage uncertainty in m plus percentage uncertainty in h plus. Because there is a power, there is a power on x. Because there is a power on x, we multiply this by 2. So this will be 2 times percentage uncertainty in x. So we substitute the percentage uncertainties, and this will be 2 plus, I think for h it is 4 plus 2 times for x, which is 5. And when you check this, 2 plus 4, that is 6 plus 10, that is 16. So the percentage uncertainty is going to be 16%. The square of the pyramid in B rests on the horizontal surface, of a bench. The square, it means the area is x squared, base area. Calculate the average pressure of the pyramid on the surface. So we know that pressure is equal to force over area, and this time the pyramid is resting on the surface, so the force it exerts is going to be the weight. It is going to be the weight divided by the area, and the weight is of course going to be mg. Then we divide this by the area. The area I said it is going to be x squared. So we shall just substitute quantities here. They gave us the mass from the table as 19.5 in grams. They have given us x as 4 centimeters. So we shall just substitute those quantities. So we have 19.5 times 10 power negative 3 to change it to kilograms. Then times 9.81. Then we divide this by x is 4.0 times 10 power negative 2 to change it to meters, but this should be squared. So we can check with our calculator. 19.5 exponent negative 3 times 9.81 divide by open brackets 4 exponent negative 2, and this is squared. So this is 119.6. 119.6. That is approximately 120 pascals to two significant figures. Okay, so I hope that is fine. One end of the spring is attached to a fixed point. A cylinder that is submerged in a liquid now suspended from the other end of the spring as shown in the figure 3.2. Now for this particular question, I cut off part A and part B because we were to see them, or we have seen such parts in other topics. But we may need some information from part A and part B, which I will just quote. So this one end of the spring is attached to the fixed point. In part A, the spring constant that we shall use, let's use spring constant as 140 newtons. Spring constant 140 newtons per meter. This was calculated in part A, but I cut it off. This is a different question. It is not relating to the one we have just answered above. So the spring constant is 140 newtons. The extension is 4 centimeters. So show that the upthrust acting on the cylinder is 0.60. Upthrust acting on the cylinder is 0.60. First of all, let's see the forces acting on the cylinder. One, there is a weight which is acting vertically downwards. Two, there is upthrust, which I'm going to call U, upwards. And there must be tension in this spring, or the force exerted by the cylinder on the spring, which is going to be the tension. So we want to show that the upthrust is equal to 0.60. Remember, the cylinder is in equilibrium. That means the resultant force on it is 0. Therefore, the tension plus the upthrust, those are the forces acting upwards, should be equal to the weight downwards. So the tension is given by Hooke's law. The tension T by Hooke's law is equal to K times extension. The spring constant, remember I said it is 140 times the extension of the spring, which is 4 centimeters. So this will be times 4 times 10 power negative 2 to change it to meters. So that is the tension. And the weight has been given as 6.2. Therefore, I just make upthrust the subject. So upthrust is going to be the weight, which is 6.20 minus 140 times 4 times 10 power negative 2. And 140 times 4 times 10 power negative 2, I think it is 140 times 4 exponent negative 2. That is 5.6. So the upthrust is going to be 6.20 minus 5.6. So 6.2 minus answer, which is equal to 0.6. So this is equal to 0.6 newtons. So the upthrust is 0.6 newtons. Calculate the difference in pressure between the top and between the bottom face and the top face of the cylinder. Difference in pressure. Remember, upthrust is as a result of difference in pressure between the top and the bottom. And upthrust force is equal to cross-sectional area times that difference in pressure. It therefore implies that the difference in pressure is going to be equal to the upthrust force. The upthrust force divided by the area, which in this case is going to be 0.60 newtons divided by the area, which area is given as 1.2 times 10 power negative 3. So we can check on our calculator. 0.6 divided by 1.2 exponent negative 3. So that gives us 500. So the difference in pressure is 500. Calculate the density of the liquid. Density of the liquid. Since we also know that pressure is equal to rho h rho g, pressure is equal to density times g times height. So the difference in pressure depends on the difference in height. But we have got the difference in pressure, so 500 is equal to the density times 9.81, then times h. Change in h. What will be the change in h? If the pressure at the bottom is due to the height h1, I mean h2, let me call it h2. It means the pressure at the bottom, which I'm going to call P2, is going to be h2 density times g. Then pressure at the top is going to be P1, and P1 will be equal to the height h1. Yes, the height h1 times density times g. It means that the difference in pressure P2 minus P1 is equal to h2 minus h1 into brackets density times g. And from the diagram, you notice that h2 minus h1 is just this height here, which is going to be 5.8 centimeters. So we come back here and say, okay, the change in height is going to be simply 5.8 centimeters, so that's times 10 power negative 2. So this is going to give us the density, 500 divided by, I'm dividing both sides by that, divided by 9.81 times 5.8 exponent negative 2. And you are seeing that we are obtaining 878.8. So density is equal to 878.8, 878.8, or approximately 880 kilogram per meters cubed. The liquid in C is replaced by another liquid of greater density. State the effect, if any, of this change on the upthrust. So above there we have seen that the tension plus upthrust is equal to weight, which means the upthrust is equal to the weight minus the tension. When we use a liquid of greater density, what is the effect? A liquid of greater density is automatically has a higher upthrust, because also we have seen upthrust is equal to area times change in pressure, which is also area times density times g times change in height. So upthrust, when the density is higher, it means the upthrust is higher. So if we have replaced the liquid with that of a greater density, we expect that upthrust increases. So here it increases. Then the extension of the spring, So it means we need to go back and look at T. From this part, we see that T is equal to U minus W, making T the subject. T is weight minus upthrust. We have seen that the upthrust has increased. but W does not change. If the upthrust increases and W does not change, it means this difference becomes smaller. Therefore, the tension decreases. So tension decreases, but remember tension is K times X tension. If the tension decreases, it means the X tension also decreases. Therefore, the X tension in the spring decreases. A pendulum consists of a solid sphere suspended by a string from a fixed point P as shown here. The sphere swings from side to side. At one instant, the sphere is at its lowest position, x, where it has kinetic energy of 0.86 joules and momentum 0.72 Newton seconds in a horizontal direction. A short time later, the sphere is at position y, where it is momentarily stationary at a maximum vertical height h above position x. The string has a fixed length and negligible weight. Air resistance is also negligible. On the figure, draw a solid line to represent the displacement of the center of the sphere at position y from position x. Of course, the curved line shows distance and displacement is a vector quantity. So since displacement is a vector quantity, we are going to look for the shortest distance between x and y. That would be a straight line between x and y. So in part A, we shall just do a straight line from the center of x to the center of y. A straight line, because displacement is a vector quantity. So you draw a straight line from the center of x to the center of y, because we are looking for the displacement of the center. Show that the mass of the sphere is 0.3 kilograms, mass of the sphere. So they have given us the momentum is 0.72 Newton seconds. Let's begin with the momentum. We know that momentum is mass times velocity, which means this is actually going to be equal to, which means 0.72 is equal to the mass times the velocity. Therefore, it implies that the velocity is equal to 0.72 divided by the mass. Also, they have given us the kinetic energy of 0.86 joules. You and me know that kinetic energy is equal to a half m v squared, which therefore implies that 0.86 should be equal to a half m v squared. So I am going to substitute for v in that expression to get m. So it means 0.86 is going to be equal to a half times m, where there is v squared. I'm going to put there 0.72 divided by m, but this should be squared also. So I open the bracket. I open that bracket, 0.86. Maybe I can multiply both sides by 2. 0.86 times 2 is equal to m times 0.72, but this is squared, divided by m, which is also squared. So this square cancels with that one. The mathematics student does not show all this algebra. So making m, there is one m in the denominator, making it the subject. So it means m is going to be equal to 0.72 squared divided by 2 times 0.86. So we check it with the calculator. 0.72 squared divided by 2 times 0.86. So this is giving us 0.301, or approximately 0.30. Calculate the height h. Calculate the height h. Let's first go back here to the diagram to see height h. I want you to note that the distance py is 0.93 meters. The distance px is also 0.93 meters. It is the same material, it is just been displaced. However, if I try to find a right angled triangle, I will draw a horizontal line which makes 90 degrees with the vertical, so that I come up with a right angled triangle. So it means this distance here, I'm going to call it D. There's no way I will find H unless I know the distance from here, from P to that point there. And because P to X is the same as P to Y, I can easily find P, I can easily find this distance here. I can easily find this distance here. And how will I find that distance? So this distance is H. That distance is going to be H. So we can say that this distance here, X plus H, should give us 0.93. But how can we find H? Let's first find H using gravitational potential energy. So calculate height H. The difference or the gain in potential energy is going to be mg times the gain in height times the gain in height. So H is going to be the potential energy. Remember, air resistance was negligible, so we can assume that all the kinetic energy has become potential energy at point Y. Therefore, this is going to be 0.86 divided by 0.30 times 9.81. The mass is 0.30. So let's first find H. So H is 0.86 divided by 0.3 times 9.81. So that is 0.292. I'll just write 0.29. So now we know the distance between, we know the height H is 0.29. That means X is going to be equal to 0.93 minus 0.29, which is 0.64. So this distance is 0.64. So let's see what happens next. The distance between point P and the center of the sphere is 0.93. When the sphere is at position Y, the string is at an angle theta to the vertical. Show that theta is 47. So since we have this distance P up to this point as 0.64 in meters, and we have Py as 0.93, so we can use adjacent and hypotenuse, and I think that is cos. Cos of theta is adjacent, which is 0.64, divided by a hypotenuse, which is 0.93. So cos of theta is equal to the adjacent. Remember, it was 0.93 minus 0.29, divided by the hypotenuse, which is 0.93. So that is going to give us theta. So 0.93 minus 0.29 divided by 0.93, shift arc cos of the answer. So that gives us 46.5. So theta is equal to 46.5 degrees, which is approximately 47 degrees. For the sphere at position Y, calculate the moment of its weight about point P. For the sphere at point Y, calculate its moment about point P. So here in this case, we are going to put We are going to put a vertical line so that we find the moment very clear. So the weight acts vertically downwards. We can extend the line of action. You notice that the perpendicular distance of the line of action from P is that one, which is the same as this distance that I called D. And that distance can be got from maybe opposite hypotenuse. That is the perpendicular distance from P of the weight. Therefore, by taking moments, the moment is going to be now, the mass is 0.30 times the G, which is 9.81 to get the force, then times the perpendicular distance. Times the perpendicular distance. We have seen that to find D, it will be opposite hypotenuse, that is sine. So it's a sine of theta is equal to the opposite D over hypotenuse, which is 0.93. That means D is 0.93 sine of theta. D is 0.93 sine theta. So this is 0.93 sine of theta, which theta is already 47. So I'll just replace this with theta, which is 47. So we can check this with the calculator. 0.3 times 9.81 times 0.93 sine 47. So that is 2.00, or just 2.0 in Newton meters. State and explain whether the sphere is in equilibrium when it is stationary at position Y. It cannot be stationary. It cannot be in equilibrium at position Y because there must be a restoring force trying to take it to equilibrium. And we have also seen that there is a resultant moment on sphere A about point P, which is 2.0. A body cannot be in equilibrium when it has a resultant moment. Therefore, the sphere cannot be considered to be in equilibrium. So we say there is a resultant moment. There is a resultant moment. There is a resultant moment acting. There's a resultant moment about point P acting on the pendulum. Acting on the pendulum, so not in equilibrium. So it is not in equilibrium because there is a resultant moment about P acting on the pendulum. Alternatively, you can talk about there is a resultant force acting on the sphere. This one tends to take it towards the equilibrium position. So there is a resultant force. There is a resultant force acting on the sphere. Acting on the sphere, so not in equilibrium. Since there is a resultant force acting on the sphere, it will not be in equilibrium. That force tends to push the sphere towards the initial position here, towards position X. That is what we call the restoring force in a unit called simple harmonic motion. State the conditions. It is a plural conditions, meaning there are more than one. For an object to be in equilibrium, these conditions are very simple. Number one, the resultant force. Resultant force in any direction is zero. Resultant force in any direction is zero. resultant torque. Resultant torque, when I talk about resultant torque, I can refer to moment. Resultant torque about any point is 0. The resultant torque about any moment, or about any point, or resultant moment about any point is 0. If those two conditions are satisfied, it means translational equilibrium is achieved and rotational equilibrium is achieved. A floating solid cylinder is attached by a wire to the seabed as shown here. So since it is attached by the wire, the weight is downwards. The tension must be downwards because the motion is most likely there is an upward force, which is the upthrust. So this is the diagram. The density of the water is 1000. The base of the cylinder is at the depth of 0.19 below the surface. The cylinder has a weight of 28 newtons and a cross-sectional area of 0.0230 meters squared. The wire and the central axis of the cylinder are both vertical. The cylinder is in equilibrium. This is very important. The cylinder is in equilibrium. Calculate to three significant figures the upthrust acting on the cylinder. So the tension must be downwards because it is fixed to the bottom and the upthrust pushes it upwards. So the tension downwards plus the weight downwards should be equal to the upthrust upwards. So if we substitute, the tension T is going to be equal to the weight, the upthrust. Sorry, the first part is telling us to calculate the upthrust. Sorry. We shall need this in the second part. The first part wants the upthrust. So upthrust, we know that upthrust is cross-sectional area times change in pressure. Therefore, the upthrust is going to be, and we know cross-sectional area, change in pressure is density times G times change in H. So the upthrust is going to be the cross-sectional area, which is 0.0230, the density, which is 1.0 times 10 power 3, G, which is 9.81, times the change in height. So the change in height is going to be the depth, which is actually 0.19 meters. So 0.023 times 1 exponent 3 times 9.81 times 0.19. So we are getting this as 42.87, or approximately 42.9. Show that the tension T in the wire is 15. So we have already seen that the tension is downwards, the weight is downwards, and the upthrust is always upwards. So we want T. So T is going to be the upthrust, which we have got as 52.9 minus the weight, which is the weight is 28. So this is minus. So this is 42.9 minus 28. 42.9 minus 28. That one minus 28. So that is 14.87, which is approximately 15. 14.87, which is approximately 15 newtons. The wire has cross-section area of 3.2 millimeters squared. Calculate the stress in the wire. Of course, we know from deformation of solids, stress is equal to strain, is equal to force over area. So the stress in the wire is going to be the force over cross-sectional area. The force, of course, is going to be the tension in the wire over the cross-sectional area, and the tension is 15 divided by the cross-sectional area. So where is the cross-sectional area? The cylinder has a weight of that and the cross-sectional area of that. I'm looking for the cross-sectional area of, oh, it is here. The cross-sectional area of the wire is 3.2 millimeters squared, so that is 3.2. To change from millimeters, this is going to be 3.2 times 10 power negative 6 meters squared. If you can't change that, just know 1 meter is equal to 1000 millimeters. So if I want 1 meter squared, I will square the other side. So it means 1 meter squared is the same as 1 times 10 power 6 millimeters squared. So to change from millimeters to meters squared, we multiply by 10 power negative 6. Okay, so the stress is going to be 15 over 3.2 times 10 power negative 6, which gives us 15 divided by, open brackets, 3.2 exponent negative 6. That is 469. 4.69 times 10 power, that is power 6, or approximately 4.7 times 10 power 6 pascals. The surface of the water gradually rises until it is level with the top face of the cylinder. State and explain qualitatively the variation of the strain energy stored in the wire as the water surface rises. Strain energy, this is going to be the elastic potential energy in the wire, which is the same as a half Fx or a half Kx squared. And F will therefore be the tension in the wire. So what happens to the elastic potential energy? So let's go back. We have seen that the tension is downwards plus the weight upwards is equal to the upthrust. What happens when the water gradually raises until it is level with the top face of the cylinder? If the water gradually rises until it is on the top, it means the upthrust at the bottom increases. The upward force is going to increase because upthrust increases with depth. Upthrust is higher at because we have seen upthrust. The upthrust force is density times g times difference in height. So if the difference in height is greater, then it means the upthrust is going to be increasing. But remember, the weight is not changing. So the weight is constant because this is tension plus weight was equal to upthrust. And it means the tension is equal to upthrust minus the weight. The weight is not changing, but the upthrust is increasing. If the upthrust is increasing and the weight is not changing, it means the tension is increasing. And if the tension is increasing, from the formula energy is equal to a half Fx, remember the tension is F. It means that the strain energy or the elastic potential energy increases since the tension increases. Therefore, we shall say upthrust on the cylinder increases. And since weight is constant, the tension increases. Tension increases, so strain energy increases. So the strain energy will increase. Define the moment of a force about a point. We know that moment of a force is the product of the force and the perpendicular distance. Perpendicular distance of the line of action from the point or from the pivot or from that point, from the point. It is force times perpendicular distance from the point, from that point. That is, or from the line, perpendicular distance of the line of action, perpendicular distance of the line of action. I think I repeated myself. Line, perpendicular distance of the line of action from the point. That is what we call moment of a force. It is not just force times distance, not at all. It is force times perpendicular distance of the line of action from the point, or the line of action of the force. Perpendicular distance of the line of action of the force from the point that we are looking at. Okay, the figure shows a type of balance that is used for measuring mass. You can look at that type of balance. So a rigged rod is pivoted about a point 2.6 centimeters from the center of a pan, which is attached to one end. The object being measured is placed on the center of this pan. So the object being measured is put on the pan in the diagram, as you can see. A spring attached to the rod 1.8 centimeters from the pivot is attached at its other end to a fixed point P. The spring obeys Hooke's law. That means F is equal to K times the extension over the full range of operations of the balance. In other words, it doesn't go beyond the elastic limit. A pointer on the other side of the pivot is set against a millimeter scale, which is a distance 5.52 centimeters from the pivot. So there's a pointer on the millimeter scale, which is 52.6 centimeters from the pivot. When the system is in equilibrium with no mass on the pan, the rod is horizontal and the pointer indicates on the scale 86 millimeters. So the pointer is indicating 86 millimeters when it is in equilibrium. An object of mass 0.472 kilograms is now placed on the pan. As a result, the pointer moves to a reading to indicate a reading of 123 millimeters on the scale. So now the pointer is indicating a reading, which I'm going to put here, that is 123 millimeters on the scale. indicate a reading of 123 millimeters on the scale when the system is again in equilibrium. Show that the increase in the length in the length of the spring is approximately 1.3 millimeters. Okay. So I think that is also easy. We are going to use simple mathematics here. Of course, it is always in equilibrium. When it is a mass is added and the pointer is there, then we can assume that this is what is happening. So the pointer is at that position, so the scale is going to be somewhere here like this. So if the pointer is there, our scale is going to be somewhere there. I'm just drawing this for illustration. This will be our scale with the mass somewhere there. So that will be our scale if the pointer is there. So you notice that the angle which the scale makes with the horizontal theta is the same angle it makes the other side theta using the rules of angles. These angles, I think they are corresponding angles. Okay, so this has changed from 123, from 86 to 123. This vertical height is therefore 123 minus 86. But the distance, the x-axis is 52.6. Then this one, the spring has also moved through, has stretched through this distance, which I will call x. But the length is 1.8. The length there is 1.8 centimeters. So we want to find x. We actually want to find x. So I will draw a simple illustration here just for understanding purposes. So this is going to be the horizontal equilibrium position, and this is another equilibrium position, but this is the pivot is somewhere here. I'm saying this angle here is the same as the other one there. But this distance was 52.5, 0.6 centimeters. And we had our spring was around here, where this distance was 1.8 centimeters up to there. So we want this distance, which is equivalent to the increase in length of the spring. We have been given a distance this side of between the initial position and the first position. This was 123 millimeters, and this was 86 millimeters. So as a mathematician, we cannot fail to do this. We can even use similarity, or we can use trigonometry. If I use trigonometry, this angle is not that, it is theta. If I use trigonometry, this distance is 123 minus 86, opposite of adjacent, that is tan. So I could use tan theta is equal to the opposite, which is 123 minus 86, divided by adjacent, which is 52.6. This is going to be the same as tan on the right hand side, opposite will be x, and adjacent will be 1.8 centimeters. That will be able to give us x. So let's now transfer that down here. So we are saying that the distance moved by the pointer is going to be 123 minus 86. So 123 minus 86, that is 37 millimeters. So we have seen from above that when we use trigonometry, the tan of theta, because the angle is the same, the tan of theta could be 37 centimeters over 52.6 centimeters, which is the same as the extension of the spring. The extension of the spring divided by 1.8 centimeters, which is the adjacent. That is tan. So when you just simplify this, you see that the extension of the spring is going to be 37 divided by 52.6 times 1.8, which is 1.266, which is approximately 1.3 millimeters. Calculate the magnitude of the moment about the pivot of the weight of the object. Moment about the pivot. We know that moment is force times perpendicular distance. So moment is going to be simply equal to, let's look for, we want moment of the weight. They have given us the mass as 0.7472, so the weight is 0.472 times 9.81, that is the weight, then times its perpendicular distance from the pivot. From the diagram, you see that the perpendicular distance of the weight which is placed there is 6.2. So it is in centimeters, just change it to meters. So it is 6.2 times 10 power negative 2. So 0.472 times 9.81, that is the weight, then times 6.2 exponent negative 2, which gives us 0.287, which is approximately 0.29. Use your answer in B Roman 2 to determine the increase in tension in the spring due to the 0.472 kilogram mass increase in tension. So we have seen the change, the magnitude of the moment about the pivot caused by the weight as 0.29. Of course, there is remember, in every position there is equilibrium. So using the principles of conservation of momentum, the increase in the tension in the spring, which I will call delta F or delta T, increase in tension times the perpendicular distance of the spring, which is 1.8, times 10 power negative 2 should give us this moment caused by the weight. Because we have added, the weight has added a moment, that moment must be balanced by, must be equal to the moment or the increase in the moment of the experienced by the spring. So this is going to be 0.29, because note that the weight is going to cause a clockwise moment, but there's a tension in the spring which is upwards. So the tension is actually causing it is going to cause an anti-clockwise moment about the pivot, the same pivot. So it means these two must be equal. The moment caused by adding a weight should be equal to the moment or the increase in tension, or the moment which causes an increase in tension in the spring. That's why I'm equating these two. Okay. So when we simplify this to find the change, the increase in tension. That will be that answer divided by open brackets 1.8 exponent negative 2, close the brackets, that is 15.95. or approximately 16. So the change in tension or increase in tension is approximately 15.95, which is 16 newtons. Use the information in B Roman 1 and your answer in B Roman 2, Roman 3 to determine the spring constant K of the spring. Give a unit with your answer. So since the spring obeys Hooke's law, then we know that F is equal to Kx, or K times extension, so the spring constant is going to be the force, which in this case we can take the increase in tension with the increase in the length. So this is going to be the increase in tension, which is going to be 16 newtons divided by the increase in length, or the distance moved by the pointer, which helped us to find, the increase in length, which was found by the distance moved by the pointer, which was 3.3 millimeters, that is times 10 power negative 3. So we just say 16, or the answer, divided by 1.3 exponent negative 3. And that gives us 12,268, which is approximately 1.22 times 10 power 4. Times 10 power 4. And which unit will I give? For tension is in newtons, then for x I've converted it into meters, so I'll give newtons per meter. State two conditions for an object to be in equilibrium. We have mentioned these conditions. Number one, the resultant force must be zero. Resultant force in any direction must be zero. Number two, so that one is for what we call translational equilibrium. Number two, the resultant torque or resultant moment. Resultant torque or moment about any point is zero. Okay. A sphere of weight 2.4 newtons is suspended by a wire from a fixed point P. A horizontal string is used to hold the sphere in equilibrium with the wire at an angle of 53 degrees to the horizontal. Calculate the tension T in the wire. So we want to find T, so I'll put a horizontal line here to help us to see that we are going to resolve carefully. So calculate T. If we want to find T, we can begin by resolving T in the vertical. T in the vertical point upwards. If I put a vertical line here, it means in the vertical it is opposite, and then T is in the hypotenuse, so that ratio is sine. So we say that sine 53 is equal to the vertical component over T. Therefore, T sine 53 is equal to that, because T sine 53 will point upwards. This is T sine 53 will be upwards. It should be balancing with the weight downwards if there is equilibrium as mentioned here. So this should be equal to 2.4 newtons. And when I press my calculator, 2.4 divided by sine of 53, we get 3.00. So T is 3.0. Then to find f, we have to resolve t in the horizontal, and t in the horizontal points to the right, which will be t cos of 53. So it means since f is to the left, it should be equal to the t cos 53 to the right, which therefore would be 3.0 cos of 53. So 3.0 cos 53 is going to give us 1.8. So that is 1.8 newtons. The wire has a circular cross-section of diameter 0.5 millimeters. Determine the stress in the wire. Determine the stress in the wire. So we have already seen that stress is equal to force over area, and this is therefore going to be the tension over the area. And remember, it is the cross section is circular, so the area is pi r squared. So the cross sectional area is going to be pi r squared, which is going to be the same as pi d squared divided by 4. So that means stress is going to be, I'm substituting pi d squared over 4 into this formula. So it will be 4 times the tension divided by pi d squared. When we substitute, we get 4 times the tension was 3.0 divided by pi, and the diameter is 0.5. So it is 0.5 times 10 power negative 3, and this is squared. So 4 times 3 divided by pi times, open another bracket, 0.5 exponent negative 3 squared, and close that bracket. So this is 1.5 times 10 power 1, 2, 3, 4, 5, 6, 7 times 10 power 7. So this is 1.5 times 10 power 7 in pascals. 1.5 times 10 power 7. The string is disconnected from the sphere in B. The sphere then swings from its initial rest position in A as illustrated here. The sphere reaches maximum speed when it is at the bottom of the string at position B. The distance between P and the center of the sphere is 75 centimeters. Air resistance is negligible, and the energy losses at P are negligible. So that the vertical distance h between A and B is 15 centimeters. We want to show that this distance is 15 centimeters. But remember, P to B is still 75 because it is the same string which moved from A to B. So P to B is still 75. If this is 90 degrees, you can think about that distance, that angle. It could be 90 plus 53, and we subtract this from 180. That angle is 37 degrees. So you could also use this as the opposite of 53 and use sine. So that sine 53 is equal to the opposite. I'll call this capital H. Opposite, which I'm calling capital H, divided by the hypotenuse, which is 75. So this means capital H is equal to 75 sine of 53. So small h is going to be the total length, which is 75, minus capital H, which is 75 sine 53. So we have 75 minus 75 sine of 53. Or you could use sine of You could use 37 degrees and find the same answer. So this is going to be 15.1 centimeters, which is approximately 15 centimeters. Calculate the change in gravitational potential energy of the sphere. I think the change is easy. Change in potential energy is equal to mg times the change in height. Since they didn't give us the mass, but they gave us the weight as 2.4 newtons for the sphere. We shall use the weight. So mg is the weight, so this is the same as the weight times the difference in height, which height is 15 centimeters. So this is going to be 2.4, which is the weight, mg, then times the height, which we have as 15 centimeters, that is 15 times 10 power negative 2. So that answer times 2.4, so that is 36. But remember it was times, okay, 15.1 exponent negative 2 times 2.4. That is 0.36. Use your answer in C Roman 1, Roman 2 to determine the speed of the sphere at B. C Roman 2 to determine the speed of the sphere at B. So if a lot of things were negligible, air resistance was negligible, and the energy losses at P were negligible, it means the loss in potential energy must be the gain in kinetic energy, or the gain in kinetic energy must be equal to the loss in potential energy. So the change in potential energy should always be equal to the change in kinetic energy if all others are negligible. Air resistance is negligible. So it means a half mv squared, that is for kinetic energy. I'm starting from the right hand side. A half mv squared for kinetic energy is equal to the change in potential energy that we have got as 0.36. Remember, the mass is going to be equal to the weight divided by g. The weight was given as 2.4 divided by g, which is 9.81. So it means V is going to be equal to 2 times 0.36 divided by the mass. The mass is 2.4 over 9.81, and this will be under the square root. I just made V the subject. So 2 times 3, I mean 0.36 divided by, open brackets, 2.4 divided by 9.81. Then we find the square root. So this is 1.7. So V is 1.7 meters per second. State the principle of moments. We know that for a body in equilibrium, the sum of clockwise moments about a given point is equal to the sum of anticlockwise moments about the same point. That is the principle of moments. So for a body in equilibrium, the sum of clockwise moments, about a point is equal to the sum of anticlockwise moments about the same point. The sum of clockwise moments must be equal to the sum of anticlockwise moments about the same point for a body in equilibrium. That type of equilibrium is actually rotational equilibrium. The body has no rotational equilibrium if the sum of clockwise moments is equal to the sum of anticlockwise moments. In a bicycle shop, two wheels hang from a horizontal uniform rod AC as shown there. The rod has weight 19 newtons and is freely hinged to a wall at end A. So the weight is at, remember, if the rod is uniform, its weight is at the midpoint. The other end C of the rod is attached by a vertical elastic cord to the ceiling. The center of gravity of the rod is at point B. The weight of each wheel is W, and the tension in the cord is 22 newtons. By taking moments about A, show that the weight W of each wheel is 14 newtons. So taking moments about A, where W is clockwise, 19 newtons is clockwise, this W is clockwise, but the other one is anti-clockwise. So using the principle of conservation, the principle of moments, the sum of clockwise moments equals the sum of anti-clockwise moments. So for the first one, we have W times the perpendicular distance, which is 0.45, plus we have 19 times the perpendicular distance, which is from B to point A, which is half of the whole length. The whole length is 0.45 plus 1.4 plus 0.75. Then we shall divide this by 2 to get half of the length. And I think this is 1.3. 0.45 plus 1.4 plus 0.75. That is the whole length. Then divide by 2 to get the center. That is 1.3. So this will be times 1.3 because the weight of the object acts at its center. Plus W times the perpendicular distance, which is 1.4. 1.4 plus 0.45. We are taking distance from every line of action of force to the point A, which is going to give us 1.85. Those are clockwise moments. This should be equal to anti-clockwise moments, which will be 22 times perpendicular distance, which is 0.45 plus 1.4 plus 0.75, which is 2.6. That is 2.6. So we can collect like terms and sum up. So we have 0.45 plus 1.85, that is 2.3 W. 2.3 W should be equal to, the other side we have 22 times 2.6, that is 57.2 minus, I'm taking this one also to the right hand side, 19 times 1.3, that is 24.7. 24.7. So 57.2 minus the answer, then we divide by 2.3. So that is 14.1. So W is equal to 14.1 or approximately 14 newtons. Determine the magnitude and the direction of the force acting on the rod at end A. Magnitude and direction of the force acting on the rod at end A. So let's say this is 14, this is 14, this is 19, but there is an upward force of 22. For translation equilibrium, the resultant force in any one direction must be 0. That means we sum up all the forces downwards, they should give us the force upwards. So the total forces downwards are 14 plus 19 plus 14. The force upwards, we have only 22, therefore there should be another vertically upward force. So the magnitude is going to be 14 plus 19 plus 14. Then we subtract the one which is in the opposite direction. So 14 plus 14 plus 19 minus 22, which gives us 25. So this is 25. So the magnitude is 25, and this should be vertically upwards to balance the total forces downwards. So that is vertically upwards. The unstretched length of the chord in B is 0.25, so this is the original length. The variation with the L of the force tension F in the chord is shown here. State and explain whether the figure suggests that the chord obeys Hooke's law. You notice that when there is no load, the length is the same as the original length. And as the load increases, the length now increases. That means extension is directly proportional to the applied load, so Hooke's law is actually obeyed. So extension is 0 when the force is 0. Extension is 0 when the force is 0 and the graph is a straight line. And the graph is a straight line, and so Hooke's law is obeyed. Extension is 0 when the force is 0. We can see that. The original length was 0.25. When the force is 0, the length is still 0.25. So it means the extension is 0 when the force is 0. And the graph is a straight line, and so Hooke's law is obeyed. Calculate the spring constant. Of course, since it is F against L against the extension, we can find the spring constant K from F over X, or we can find it from the gradient, which is going to be on the vertical we have 60 minus 0, 60 minus 0. On the X we have 1.00 minus 0.25, which is 60 divided by 1 minus 0.25, which is 80. So K is 80 newtons per meter. On the figure, shade the area that represents the work done to extend the chord when the tension increased from F equals to 0 to F equals to 40. So work done is the area under the graph. F equals to 0 to F equals to 40. F equals to 40 is here. So the area under the graph, we shade this part here. So that is the area that we are shading, which represents the work done to extend the chord from F equals to 0 to F equals to 40 newtons. Define the moment of a force. So we have said this is force times perpendicular distance. Force times perpendicular distance of the line of action of the line of action of the force. Line of action of force from the pivot or from the point. Force times perpendicular distance of line of action of the force from the point or to the point. Let me use to the point. Perpendicular distance of the line of action of the force to the point. Don't tell a story when you are defining moment. It is just force times perpendicular distance of the line of action of force to the pivot, to the point, which is normally the pivot. Determine the SI base units of the moment of force. So, since moment is force times perpendicular distance, therefore the units are going to be for force, kilogram meters per second squared, and for distance, that is meters, and that gives us kilogram meters squared per second squared. A uniform rigged rod of length 2.4 is shown in the figure there, the cross-section area A. The rod has weight 5.2 newtons and is made of wood of density 790 newton kilogram per meter squared. Calculate the cross-sectional area A in millimeters squared of the rod. Cross-sectional area. So they have given us the weight, they have given us the density, meaning we can relate this to the volume. So weight is equal to mass times acceleration of free fall. But we know that mass is density times volume, so that is times acceleration of free fall. And we know that volume is going to be the cross-sectional area times the length of the material. So this is volume, then times G. Now it becomes easier for us to find the area. So it means the area is going to be equal to the weight divided by density times the length times G. So the area is going to be equal to 5.2 newtons divided by density, which is 790, times the length, which is 2.4, times G, which is 9.81. 5.2 divided by, open brackets, 790 times 2.4 times 9.81. So that is 2.795 or 2.9. Sorry, 2.8. 2.8 times 10 power 2.8 times 10 power negative 4, that is meters squared. But we want the answer in millimeters squared. Remember, 1 meter is 1,000 millimeters. So 1 meter squared, we also square the other side. That is 1 meter squared is the same as 1 times 10 power power 6 millimeters squared. So to convert from from meters squared to millimeters squared, we have to divide by, we have to multiply by 10 power 6. So the area is going to be 2.8 times 10 power negative 4 times 10 power 6. So the area is going to be 2.8 times 10 power negative 2 in millimeters squared. No, not power negative, power 2 in millimeters squared. A finishing rod AB made from the rod in B is shown in the figure. So that is the finishing rod. End A of the rod rests on the ground and a string is attached to the other end P. A support stick exerts a force perpendicular to the rod at point C. The weight of the rod acts at point D. The tension T in the string is in a direction perpendicular to the rod. So the tension is in perpendicular. The rod is in equilibrium. That means there is no resultant force, there is no resultant moment. And inclined at an angle 45 degrees. The forces and the distances along the rod of points A, B, C, and D are shown. Show that the component of the weight perpendicular to the rod is 4.3 newtons. So we need to resolve the weight perpendicular, that is at 90 degrees to the rod. So I'll draw a line which makes 90 degrees with the rod somewhere here. So we are going to resolve perpendicular because this now makes 90 degrees with the rod. So if it makes 90 degrees with the rod and the angle between the weight and the rod is 56, it means resolving using 56 to our line that we have drawn will actually be sine. Alternatively, we could find the angle between our new perpendicular line and the weight. In that case, we would use cos. Therefore, the component we are looking for is going to be equal to the weight, which is 5.2. Since I'm using 56, that will be sine 56 degrees. So 5.2 sine 56, that is 4.3. By taking moments about end A of the rod, calculate the tension T. Taking moments about end A of the rod, calculate the tension T. So you notice that the weight is causing anti-clockwise moment. T is going to cause anti-clockwise, but this 4.6 will cause clockwise. So by taking moments, if it is in equilibrium, the sum of clockwise moments is equal to the sum of anti-clockwise moments. All we need is to find the perpendicular distances. For T, perpendicular distance is 0.6 plus 0.6 plus 1.2, which is 2.4. For 4.6 newtons, the perpendicular distance is 0.6 plus 1.2, that is 1.8. And then for weight, we have got the component, which is 4.3, and the perpendicular distance is just going to be 1.2. So now we have now taken moments. So T times its perpendicular distance from A, which is 2.4, plus 4.3, that is the component of the weight, and its perpendicular distance to 1.2, which is equal to 4.6 times the perpendicular distance, which we have seen as 1.8. So we just find T, that is 4.6 times 1.8 minus, open brackets, 4.3 times 1.2 divided by 2.4. So we notice that the tension T is going to be 1.3. So that is 1.3. A cylinder is suspended from the end of a string. The cylinder is stationary in water with the axis of the cylinder vertical, as shown here. The cylinder has weight of 0.84, height h, and a circular cross-section of diameter 0.031. The density of the water is 1.0 times 10 power 3. The difference between the pressure on the top and the bottom faces of the cylinder is 520 pascals. Calculate the height h of the cylinder. So we know that difference in pressure is equal to density times g times difference in height h. So 520 is going to be the density, which is 1000 for water, times g, which is 9.81, then times h. So you can find h 520 divided by 1000 times 9.81. That gives us 0.053. 0.053. Show that the upthrust acting on the cylinder is 0.39. Upthrust acting on the cylinder is 0.39. So the weight of the cylinder is downwards, I'll quote W. The upthrust is upwards, I'll quote U. Then the tension is also upwards, I'll quote T. But we know that upthrust is equal to the cross-sectional area times change in pressure. So upthrust is equal to the cross-sectional area times the difference in the pressure between the top and the bottom. So this is going to be, remember the area is equal to cross-section, pi r squared, which is pi d squared over 4 if we remove the radius. So it means the upthrust is going to be the area, which is pi d squared over 4 times the difference in pressure, which is going to be equal to pi. The diameter was 0.031, so that is 0.031, but that is squared divided by 4 times the difference in pressure, which is 520. You can just check and see. 520 times pi times 0.031 squared divided by 4. So this is giving us 0.39. So the upthrust is equal to 0.39 as required. Calculate the tension T. So we have seen that the tension T upwards plus the upthrust for equilibrium should be equal to the weight. From the diagram, you can see the tension and the upthrust. So it means that the tension is going to be equal to the weight, which weight is, the weight is 0.84, 0.84 minus the upthrust, which we have got as 0.39. So 0.84 minus 0.39, which gives us 0.45. So this is 0.45. The string is now used to move the cylinder in a vertically upwards through the water. So the motion is vertically upwards. The variation with time t of the velocity of the cylinder is shown in the figure. So the velocity increases, all of a sudden it decreases. Use the figure to determine the acceleration of the cylinder at t equals 2.0. T equals 2.0. So this is a straight line, so we can find a gradient. So acceleration is equal to change in velocity v minus u over t, or that is simply change in velocity over t. So I can just take a 2 I think that is 8.0. So I'll say 8.0 times 10 power negative 2 minus 0, of course, divide by 2.0 minus 0. I'm just finding the gradient. I could also have used the 10 minus 0 over 2.5 minus 0 because it is a straight line. The acceleration is the same, the gradient is the same everywhere. So this gives us 8 exponent negative 2 divided by 2, which gives us 0.04. 0.04, or it is 4.0 times 10 power negative 2. The top face of the cylinder is at a depth of 0.32 meters below the surface of the water at time t equals to 0. Use the figure to determine the depth of the top face below the surface of the water at time t equals to 4 seconds. So at time t equals 4 seconds, we can find the total distance, which is the area under the graph. So distance is equal to the area under the graph. And the area under the graph is going to be a half times. So we look at the graph. You can take it as one triangle whose base is 4, or you can divide it into two triangles. I'll just take it as one triangle whose base is 4 seconds. So this will be 4.0. Then times the height. What would be like the height is this value here, which is actually 10.0. So this will be times 10.0, but remember on the vertical we have centimeters per second. So this will be times 10 times 10 power negative 2 to change it to meters per second. So this is going to be 4 times 10 exponent negative 2. Then divide by 2. So that is 0.2. So the distance is 0.2 meters. That is the distance moved in that time. But remember at t equals to 0, the top face was at 0.232 meters below the surface. And it has moved the distance of 0.2 meters upwards. That means the depth is the difference. The depth is going to be equal to 0.32 minus 0.2. 0.32 minus that answer, which is 0.12. So the depth is 0.12 meters. The cylinder in B is released from the string at t equals to 4 seconds. The cylinder falls from rest vertically downwards through the water. Assume that the upthrust acting on the cylinder remains constant as it falls. State the name of the force that acts on the cylinder when it is moving, that is friction, and does not act on the cylinder when it is stationary, that is friction, and in a fluid we call it the viscous drag or viscous force. We call the viscous force. State and explain the variation, if any, of the acceleration of the cylinder as it falls down through the water. The acceleration, because the upthrust is constant and the upthrust is upwards. Of course, the tension is also upwards, but then the weight is downwards. Now the tension is reducing as the cylinder is falling downwards. The tension is increasing as the cylinder is falling downwards. And since they say the upthrust remains constant, it means the viscous force is going to increase with the depth. The viscous force, which is the dragger force, is going to increase with the depth. It actually increases with the depth because as the speed increases, the water resistance also increases. So the viscous drag increases. And if the viscous drag increases, it means the acceleration reduces. The acceleration decreases until a point where it becomes 0. That is when the upthrust is actually equal to the weight. So viscous force increases with speed or depth. Viscous force increases. Viscous force increases with the speed or with depth. But more importantly, it increases with the speed. It's like air resistance. Air resistance increases with the speed. And if air resistance viscous force increases with the speed, it means the resultant force decreases. So the resultant force decreases. Resultant force decreases, hence acceleration decreases. Hence the acceleration decreases. So that is what we could that's the explanation we could give for that for the variation of acceleration as the cylinder falls down. The viscous force is going to increase as the speed increases, and there will be a point where the upthrust is equal to the weight. At that point, since the upthrust plus viscous force equals to the weight, the resultant force will be zero. That means the acceleration decreases to zero. Because the resultant force decreases, the acceleration is going to decrease. Okay. I hope that has been useful. For part one, I would like to stop here. I have a lot of flaws that is affecting me from recording this video very well. So see you in part two. For now, let's stop at that point. Bye bye.